big handout to do with logarithms. So let's finish that first. So it's the one that we identified the different methods of techniques to address the different problems, whether you use logarithmic differentiation, just use the properties of logarithms, just the chain rule. So these are the last 2 pages, I think, of the handout. And did we do the first one? Yeah, okay. Yeah, we did that one. So we're starting with the second one, which is we've talked about using the properties of logarithms a lot. We haven't actually done a lot of it. I mean, we haven't followed through the whole thing. So what we want to do is this problem right here. Let me go ahead and delete this page. So this is an example of using the properties of logarithms to find the derivative. So what you want to first do is to rewrite this as it'll be 3 terms instead of 1 term, and the product of two terms in a logarithm is the same as the addition of the 2 terms separately, and if you have something in the denominator, you subtract that. And then you can use this as the half power, change this to the half power, and then pull that outside the logarithm, as well as this term where you have the cubed. You can pull the 3 outside of the logarithm, and then you can just use the chain rule to find the derivatives once you find the derivatives. So first thing you'll do is use the properties of logarithms to break that apart, and then you'll take the derivatives. The only one that will be really other than trivial is this one, because it has x squared in the argument. This one's just x plus 2, so that'll, when you take the derivative of the natural log of x plus 2, you just get 1 over x plus 2. And if you take the derivative of the natural log of x, you get 1 over x. This one, you got a little extra stuff you got to worry about. So it's going to be 1 over the argument, and then take the derivative of the argument. That's the chain rule. So go ahead and start on that one. And while you're doing that, I'm going to hand out another thing we'll work on afterwards. So I made a new handout for this year. So don't forget to, well, okay, yeah, when you make sure you put that in parentheses so we know that it's the logarithm of the whole thing. So that's the one you got to use the chain rule on, and so it's going to be 1 over that. So it's when you take the derivative of the natural log, you get 1 over u, and then you multiply it by u prime of x. So you just take the derivative of x squared plus 1 and multiply that by 1 over x squared plus 1. Yeah, it looks like now if you want to go on to the next one, whatever that one is, I think using logarithmic differentiation. So you'll need to take the logarithm of both sides and then just do what you just did. So yeah, you're going to have to show me how to use I haven't decided what I'm doing about your calculators being actually able to do the derivatives. I thought it was the next version up that actually did that. Mine might not actually do it. That's why I don't know about it. So obviously, if you don't know the steps in between, I'm not going to accept it anyway. So it's not like you can get by without not knowing what you're doing. Some people try that, but usually it's pretty obvious. I had this guy, I think it was the first or second year I taught the class, and he came and argued with me about, well, can't I just use my calculator? I mean, why do I have to learn this stuff if it does it automatically? I'm like, give me a break. He ended up dropping the class. By the way, was it last year that Mr. Appel was around crutches for part of the year? Yeah, he's starting to hobble around a little bit right now. I'm worried that his So the first thing I did, well, I made the square root to the 1/2 power, the argument to the 1/2 power. And then I broke it up into 3 parts. The natural log of x squared plus 1 to the 1/2 power plus the natural log of x minus the natural log of x plus 2 cubed. And then you can bring out the exponents. So that's the simplifying part. And then when you take the derivative, you get 1/2. And then you take 1 over the argument of the natural log times the derivative of the argument. The next one, you don't have to do anything except just write 1 over x because it's just x. And then the last one, you get 1 over the argument times the derivative of the argument, which is just 1 in this case. So when you have just x, or you have x plus or minus something, it's just 1 over that thing. In this case, I don't have to use the chain rule because I just have x. But if I have something other than x, theoretically I should use the chain rule, but it ultimately ends up just being 1 over that. Some people kind of get complacent and they think it's always just 1 over the argument, but it's always 1 over the argument of the natural log times the derivative of the argument. So then you just clean it up a little bit so you can cancel the 2's out. So you end up with x divided by x squared plus 1 plus 1 over x minus 3 divided by x plus 2. Okay, so that's the first problem. So the next problem, you're going to, because you don't have, I apologize for being so fuzzy, but in this we don't have the right-hand side already as a logarithm, but it's a complicated enough expression that it makes sense to use the properties of logarithms to simplify it. So that's why we're going to take the logarithm of both sides and then use the properties of logarithms to simplify the right-hand side, just like we did in the previous example. And then take the derivative. Then you've got the extra step, that involves where you've got to, plug this back in ultimately because of the way the left-hand side works. So let's just so go ahead, and first step is just to take the natural log of both sides. And then simplify the right-hand side using the properties of logarithms. Yeah, so now you multiply it by y, so this whole thing gets multiplied by y, and then you're going to substitute y back in.
Get multiplied by y, or just what's on the inside?
Well,
Y would go here, right?
Yeah, everything's going to get multiplied by y, but best thing to do is just stick y out on the outside and then plug it in. Yeah. Okay.
Can you do that?
What you have to do is take the 1/2 out at first, and then So you'll have 1/2 times the natural log of that ratio, and then you'll break it up into it. So both of them will be, you'll end up having both multiplied by 1/2 because they're both part of that square root thing.
But does the second one have to be multiplied by -1/2 since it's in the denominator?
Right. Yeah. So that is correct. So you've done it in two things in one step. Normally you might take the half out first and then break it apart. But as long as you know what you did there, and it wasn't just luck. Yeah. Okay. So you can see I did it slightly different than some of you guys. I didn't leave out this. Sometimes I do, but this case I didn't. I didn't leave out that intermediate step, and that's because I ended up multiplying the whole thing by 1/2, which ultimately ends up meaning you multiply each one by 1/2. Okay, so that's the simplification. The next thing you do is you take the derivative of both sides with respect to x. So the left-hand side, you're going to use implicit differentiation, and on the right-hand side, you just use normal differentiation. And, we should know how to do these because we just did them in the previous problem. This first term was that x squared plus 1, and we got that result. So you should be able to do those two parts reasonably easy. And then remember, the implicit differentiation is going to give you 1 over y times y prime. So then you'll multiply both sides by y, and then you'll substitute in the original expression for y, which is up there, to get the whole derivative in terms of x. Okay, so you cancel out the halves. Well, yeah. Did you do that? Oh, oh, you got them right there. Okay, I see where they are. Yeah. Okay, so now just multiply both sides by y to solve for y prime. Okay, so you now multiply both sides by y.
Yeah.
Okay, they're over here. Yep, okay, now, and then you plug that back in. Okay, yep, that's fine. Okay, did you simplify it a little bit?
Yeah, I multiplied it by y and then
Yeah.
canceled this out and added that to that.
Yeah. Okay. Yep. So there's your answer. So we took the derivative of everything with respect to x. So that gave you 1 over y times y prime on the left-hand side. And we got 1/2 times 1 over x squared minus 1 times the derivative of x squared minus 1 minus 1/2 times 1 over x squared plus 1 times the derivative of x squared plus 1. Cancel out the 2's, and you end up with x over x squared minus 1 minus x over x squared plus 1. And then you multiply both sides by y, and then you plug y back in. Now the question is that good enough for a test solution? The answer is yes. Okay, but if you wanted to simplify it, what you would have to do is combine these two. So you'd have x times x squared plus 1 minus x times x squared minus 1, all divided by x squared minus 1 times x squared plus 1. And that whole thing times x squared minus 1 over x squared plus 1 to the 1/2 power. And then you could combine the terms of the numerator. You're going to have x cubed minus x cubed. So these two cancel out, and you'll have x minus a minus x. So you end up with 2x in the numerator. And in the denominator, you still have x squared minus 1 times x squared plus 1. And you multiply by x squared minus 1 to the 1/2 power divided by x squared plus 1 to the 1/2 power. So you would get these, you can simplify here. So ultimately what you end up with is 2x times, so this in the numerator and this you have to the first power here. So you'd end up with x squared minus 1 to the 1/2 power. And then you'd have x squared plus 1 times x squared plus 1 to the 1/2 power. That would be x squared plus 1 to the 3/2 power. And then you could probably change it back to the square root. So you'd end up with 2x over the square root of x squared minus 1 times x squared plus 1 to the 3/2 power. But as long as you get to the point where the only part left would be some algebra, that's fine. Did I get that all right? Everybody? So what you got, Margaret? Because you did it. You simplified it. So. Okay, now the next one. What's the next one? So this one is a U substitution problem. So, how would you recognize that you were supposed to use the integral of 1 over u du? Well, because usually one of the key things is all of the other U substitutions that we've dealt with is we've had the square root of something. We've had something raised to a power in the denominator and the numerator. Or we've had the sign of something. So in this case, there's nothing raised to a power. We just have a polynomial in the denominator, not raised to any power, or not square root. So that would, your first guess would be, maybe it's one of those where I make the entire denominator u, and that's what the case is. So the only other option that we have right now, we actually haven't covered yet. So if you see something like this, most likely it's going to be where the denominator is u. So make the denominator u, calculate du. It's not going to be exactly, there's going to be a factor of 3 or something like that you'll have to deal with. Ultimately, the substitution will be some constant times the integral of 1 over u du, which is going to be the natural log. The integral of 1 over u du is the natural log of the absolute value of u. The reality is, well, yeah, that was an interesting conversation. I was talking to Scott Peterson yesterday about chemistry. He was talking about how hard to make chemistry. because you've always got that question of, is it a real college course? If we gave you real college courses in high school, you would die. Okay, so he said he remembers as a freshman in college spending like 75 to 80 hours a week on school, and you don't have that amount of time. So how do you make it so that it's kind of like a college course, but not quite terribly like. And the reason I bring that up is recognizing integrals like this, you've just got to do a lot of them, and we just don't have time. You don't have time to do enough of them for most people to feel comfortable. It's just it's the bottom line is there's no easy way. You just have to do a lot of them, and then all of a sudden you're like, you get good at them. I'm still waiting for my trumpet experience. I'm getting frustrated with my trumpet because I've reached a plateau, and it seems like I'm not sure how I get further. Mostly my range and my stamina. Like I keep hoping that there's going to be a breakthrough, but I know that doesn't. When I learned to play the guitar, I've kind of reached a plateau there, and I've realized that either I'm not going past that plateau, or the amount of work that I have to do to get to the next level I'm not willing to do. So, yeah. By the way, you can come and hear us again. They have the Clifton Forge Christmas Parade on Friday, and afterwards in the Masonic Theater they're going to have a carol sing-along, and we're going to be the group that leads. We're not singing, but we're going to be playing the melody so that you guys can sing. So that's our latest Christmas gig. Oh, actually, this is wrong, isn't it? Yeah. Okay. It's x squared plus 1. Sorry. Yeah, I need to fix that. I remember I did that last year and I forgot about it. So how many people realize that I messed it up? Okay. Yeah. So if you ever see something like that, especially on a test, I try my best not to mess up a test, but let me know. My math for the liberal arts class, I gave a test before the exam, and they had to find unknown angles. There were all these lines drawn together, and I forgot to show the two lines were parallel. And most people assumed that they were parallel, but I'm sure there were people in the classroom that probably thought, well, they look parallel. I have to know they're parallel to do it, so I'll just do it. I would have, been nice if somebody said, "Hey, are those lines parallel?" And I would have gone, "Oh yeah, you're right." Okay. So if you ever see something like that, don't hesitate to. I used to do that. I don't know why, because normally I wasn't I'm not an outgoing person, a kind of shy person. So, but I did have this tendency to ask questions that I knew the answers to, but I knew the other people didn't know the answers to. So I was like, I know these people don't get that, so I'm going to raise my hand, because they weren't clear about something, like. I don't know if that was annoying or not, but I did it anyways. Okay, and the last one is just to remind us that we now know how to integrate all of the trig functions. So you would go to your table for this one. You still have to use u substitution because I don't just have the cosine of x. So u would be 2x, but pull out your sheet and look up what the integral of the cosecant is. And, so ultimately you'll end up with the cosecant of u. It involves the natural log. So I think it's the natural log. Is it negative the natural log, the absolute value, the cosecant of x plus the cotangent of x? I'm not sure if the minus sign's there. I didn't bring my paper. What is it? It's the negative. Okay. Yeah. Oh, I made a mistake. Yeah, I committed one of those cardinal sins here, which was to change the argument of the trig function. That's why I realized I'd messed up. So in your sheet, you'll find the integral of the cosecant of u as negative the natural log of the absolute value of the cosecant of u plus the cotangent of u. And then I plug u back in. The thing is, anytime you have a trig function that has an argument other than just x, when you take the derivative, you always end up multiplying by that coefficient. So if you had, the sine of 2x, then the derivative of the sine of 2x would be the cosine 2 times the cosine of 2x. The argument never changes. So don't ever, when you do these problems, go back to your original problem. Make sure that this is always the same. The only way that we can change this to something other than 2x or whatever it is by using a trig identity. You can never change the argument of the trig functions through differentiation or integration. can only do it using the trig identities. And when you integrate, you always divide by, you should end up dividing by this constant. So wherever it was the original integral, the integral of cosecant of 2x, we should divide by half. If we took the derivative, we should multiply by 2. Okay, so that's that handout, so you can turn that in after class. Instead of going to the handout I gave you today, I'm going to give you some new material. And I think this is section 5. And then we'll come back on Thursday and we'll go over the handout I gave to you today. So what do we know? Let's review what we know so far, what we've learned up to this point. We've learned that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. We've learned that the integral of e to the x dx is e to the x plus c. We know the derivative with respect to x of the natural log of x is 1 over x. And we know that the derivative with respect to x of e to the x is equal to e to the x. We also have those integrals. We know what the integral of the tangent of x is. We know what the integral of the I don't know off the top of my head, but we figured these out. So we had those as well. We also know the integral of the cosecant of x. That's something. That's the one we just did. And we also know what the integral of the secant of x is. We did that. So we have these. How many formulas here? 8 new integration and differentiation formulas. Yeah. Okay. So the question is, what is the derivative with respect to x of log to base a of x? So if we have a logarithm that's some other base than e, log to the base e is the natural log. Everything we've done so far is natural logs. But let's say we use log base 10 a fair amount. For example, pH scale. The pH scale uses logarithm to base 10 of the ratio of something or other to something or other, some hydrogen thing, hydrogen ions or something like that. So there are other logarithms. It's very rare in practical situations that we use any other logarithm to a base other than e or to 10, but we're going to learn how to do it anyway. So how do we do this? Well, what we do is we use the properties of logarithms. So we're going to take the original question, what is before we take the derivative, we're going to use the properties of logarithms. And the one we haven't used is the change of base formula. So do you remember, anybody remember what the change of base formula is? Let's say if you want to do log base 10 of a. So if we know if we have the information in log base 10, but we don't have it in log base a, and that's incorrect. Let me fix that. So if we know it in log base 10, which we have in our calculator, we also have natural log. What you do is you take the log to base 10 of the value and divide by log to the base 10 of a. So let's just try that out. So let's say we want to know what the log to the base 5 of 7 is. That's the log to the base 10 of 7 divided by the log to the base 10 of 5. And if you pull out your calculator, and do that. We'll do them separately. We're not going to do them in one fell swoop here. But so if you take log base 10 of 7 and you divide by log base 10 of 5, you will get 1.20906. So how do we know if that's true or not? Well, if you take 5 to the 1.20906 power, you should get 7. So let's try that. 5 to the 1.20906 power is 7. Okay, so that is true. So it's easy to, if you don't have log to the other bases on your calculator, you can use this change of base formula, which we do know log base 10. And I checked it because all calculators, pretty much all calculators have exponents. And because that's what the log base 7 means. What power do I raise 5 to get 7? Well, I raise 5 to the 1.20906 power, and that gives me 7. But we're not going to use log base 10 in our derivation. We're going to say log base a of x is equal to the natural log of x divided by the natural log of a. So what I'm doing there is I'm taking log to the base e of x divided by log to the base e of a, which is log base e is just natural log. So that's the prop. I'm using the change of base formula for logarithms. So when I say I want to take the derivative with respect to x of log base a of x, that's the same as saying I'm going to take the derivative with respect to x of log or natural log of x divided by the natural log of a. But a is just the base. It's a constant. So I can take that outside the derivative. So I get 1 over the natural log of a times the derivative of the natural log of x with respect to x. Well, that's just 1 over x. So I get 1 over the natural log of a times 1 over x. So my new formula here. If you have an exponential that is any base other than the natural log, so the derivative with respect to x of log base a of x is equal to 1 over the natural log of the base times 1 over x. So now we have another formula. So let's just do an example. Let's say y equals log base 3 of x plus 1. What is y prime? Well, I just use the formula. Y prime is equal to 1 over the natural log of 3. That's my base. 1 over the natural log of a times 1 over x plus 1 times 1, because I take the derivative of the argument. So the final answer is y prime is equal to just 1 over the natural log of 3 times 1 over x plus 1. So it's not surprising that the integral of log base a of x dx is going to be equal. No, they can't do that one. Actually, there is no equivalent the other way. Okay, we don't have to worry about that. Okay, so we just have a derivative formula. We won't know how to. This one, don't write it down. we'll have to wait till chapter 8 to know how to do this. Okay, so not now. Because we don't know how to do this right now. We know what the derivative of the natural log is, which is 1 over x. And we know the integral of 1 over x, which is the natural log, but we don't know how to do that, and we won't know it until chapter 8. So let's see, what else is there? So let's say, what is the derivative with respect to x? Well, we know what e to the x is, right? The derivative of e to the x is e to the x. So the question might be, what is the derivative of a to the x? Where a is any base, not just 2.171828. So what you do here to derive this one, you use logarithmic differentiation. So let's do it. So we'll go to the next page. So we'll say y is equal to a to the x. What is y prime? So you take the natural log of both sides. Use the properties of logarithms to simplify. So we did that earlier when we derived what the derivative of e to the x was. Then you take the derivative with respect to x of every term. Now this is just a constant again. So let's just go ahead and pull it outside the derivative. So we get the natural log of a times the derivative with respect to x of x. And now we take the derivative. So we get 1 over y times y prime is equal to the natural log of a times 1. The derivative of x with respect to x is 1. You multiply both sides by y. And then you substitute y back in. So that's the formula. So let's just write it out again. So that says the derivative with respect to x of a to the x is just the natural log of a times a to the x. So the only difference between the derivative of e to the x and a to the x is that you just have to multiply the original exponent by the natural log of the base. You know, if a is e, I get the natural log of e, which is 1. And so for the special case of a equals e, it defaults back to the original derivative we came up with the other day. So this is really, that's our next formula. That's the derivative. So let's put a square around that one. Okay, now we do have the question of what is the integral of the a to the x. So let's do that one. Well, it wouldn't be surprising if you thought, well, I have the derivative of a to the x is natural log of a times a to the x, so the integral of this is going to be that. So you can, I don't think it's too far stretched to realize that the integral of a to the x is 1 over the natural log of a times 1 over, wait to make sure, no, that's wrong. Just not 1 over, it's just a to the x plus c. So that's the integral formula for integrating an exponential function that has a base other than e. And again, if you let a equal e, you'll get 1 over the natural log of e. The natural log of e is 1, so it defaults back to the one that we know. So this one, when you take the derivative, you multiply by the natural log of a, and when you take the integral, you divide by the natural log of a. Sort of like we were just talking about with the cosecant. You know, if you take the derivative of the cosecant of 2x, your answer is going to be 2 times something. And if you take the integral of the cosecant of x, you get 2x, you get 1/2 times the answer. So those are the formulas for logarithms that are base other than e, and the derivatives and integrals of exponentials where the base is something other than e, and you just have these factors of the natural log. Either you divide by the natural log or you multiply by the natural log. Okay, so we'll play around with that on some examples. Actually, we're going to go and start working on our handout that I gave you today. It's just some more practice. So the first problem, let me write it down for you. You've already got it, but let me just put it on the board. And let's go back, and where's my list of formulas? There we go. So here's our formula list. So the first question is, if y is equal to e to the 3x squared plus 1, what is y prime? So you basically have to use the chain rule. If you go to your formula sheet, you'll see that the derivative with respect to x of e to the u is equal to e to the u. That's it. Okay. But you've got to use the chain rule. So you'll take the derivative will be just this times the derivative of the exponent. So that shouldn't take you very long to do. So think about that. Anytime you see e to something other than x, just write down the original e to whatever it is and multiply by the derivative of the exponent. Okay. So when I would do this problem, I would think, okay, it's e to the something. So I know that I remember him saying you can't change the argument of trig functions and you can't change the argument of exponentials when you take the derivative. So you still have e to the 3x squared plus 1, and then you multiply by the derivative of the exponent, which is going to be 6x. So that's the answer. Okay. You could do it the long way around, where f of u is equal to e to the u of x is equal to 3x squared plus 1. Do it that way, but ultimately just write down the original expression and then take the derivative of the exponent, multiply them together. Okay, the next one is just using the product rule. So we got, that's the reason I called it h of x. So remember, the product rule says you take the first term, multiply by the derivative of the second term times the derivative of the first. And you should be able to do both of those derivatives in your head, because we just talked about that. When you take the derivatives, you multiply by the derivative of, if it's just a simple case like that, you're going to multiply by 2 when it comes to the sign, and you're going to multiply by -1 when it comes to the exponential. But in the case of the trig functions, it does change from sine to cosine. In terms of the exponential, it just stays the exponential. So see if you can do that without writing everything out. Just think about what we talked about. The derivative of the sine is the cosine. When you take the derivative, you multiply by if it's just a simple coefficient constant times x, it's just that constant times the derivative of whatever that is. And You don't change the argument of the trig functions, and you don't change the exponent for the exponential function. So there you go. First term times the derivative of the second. You've got a negative sign, so that's, notice this doesn't change. You just multiply by the coefficient in front of the exponent, which is -1. Then you take the derivative of the first term, which is going to be 2 because you've got 2x. The derivative of the sine is the cosine. Don't change the argument. And then multiply by the second term. And then I've done a little I want to move this down so I can point to it on the board here. That's probably too low. Not quite that low. There we go. So here's the hierarchy again. The sign is always out front. Okay. Exponentials are always before signs. So it's kind of what we've done is we have the sign plus or minus. You have any constants. That's next. If there were any polynomials, x squared, you put those next. The next one is the exponential function, and finally is the sine function. It just goes a kind of complexity, because e to the x is actually a little simpler than the trig function, because when you take the derivative of e to the x, you get e to the x, whereas when you take the derivative of the sine, you get the cosine. So something changes there. So these are both non-polynomials, but this one's a simpler non-polynomial than that one. So that's okay. So the next one, we're just using, this. Let's go back to our list of formulas. We're just using this one, using u substitution. So u, obviously, to make this thing work, has to be the exponent. And x plus 1 has to be some multiple of, or I shouldn't say x plus 1 times some number has to equal the derivative of the exponent for the whole thing to work out. And it does. So go ahead and do that one using u substitution. So I forgot to write it on the board. Here we go. But you have it. So I'm going to come around to be nitpicky about your format of your DUs and all that kind of stuff. So. Yeah, don't forget your parentheses around 8x plus 8. There you go. So there's your answer. So when you take the derivative, if you factor out an 8, you have x plus 1 dx times 8 is du. So you divide by 8. So substituting for u is this, x plus 1 dx is du divided by 8. Factor out the 1/8. Integrate e to the u du, which is e to the u plus c. Plug u back in, and you're done. Okay, so we'll continue on this on Thursday.